Okay, let's get started. So today I'm going to talk about some content related to path planning, especially using RRT, RRT star, and the A star algorithm. Okay, so again, so this is a course, as a second part of the career core courses following AR 1216. So in this course, we're going to focus on dynamics and also path planning and other methodology applied to quadrotors. So this is the outline of this lecture. I will first go through the motivation of this course, and then I will introduce the background of RRT, RRT star, and A star algorithms. So I will later upload all the related code on Quarkus, and you can also download all the code from my GitHub link. So the planning is used for generating a path for quadrotor controller after following a specific mission requirements. For example, the planning should have the capability of generating optimal or suboptimal paths while achieving obstacle avoidance. So when you go through the backgrounds of planning, usually people mention the two method terminologies. One is motion planning, another one is path planning. So for motion planning, it involves generating a precise trajectory involving position and the derivative of positions, as well as equilibrium control inputs to the robot. So it's more like a precise description of how robot moves from one point to another. But path planning, on the other hand, is a subset of the motion planning. So in this case, we only care about the position of the robot from one point to another. So we're basically generating a sequence of position points connecting the starting position and the end position, so that the robot can just follow the waypoints to get the final destination. Okay. So in path planning, the areas of path planning, there are two main categories of method. One is so-called search-based method. So in this category, there are some famous algorithms such as the A star, the just class algorithm. So basically, those methods requires you to construct some kind of cost function, and the algorithm will then perform either depth first search or breadth first search based on these cost functions to find out an optimal path. So it's a very systematic way to generate optimal paths. Sample-based methods, on the other hand, use random sampling. So we just take a random sample in the state space and grow a tree-like structure to form the path. And then in the random sampling process, we hope that the random samples will explore the entire state space and will eventually reach our goal. So the very typical method of sampling-based method are rapidly exploring random tree, RRT, which are going to be the main topic of this lecture. And there are some other methods such as a probabilistic roadmap. It's called RPM. Okay, so the first module of today's lecture is rapidly exploring random tree. It's called RRT, and a modified version of the RRT called RRT star. So RRT is a sample-based algorithm. So it takes sample in the state space, and then by using some methods, we are going to connect all the samples into a tree-like structure, and then eventually we'll form the path based on those sample points. This method was developed in 1968 by Stephen Novell and James Cooler. So used to handle the problems with obstacles and differential constraints. It's also widely being used in autonomous robotic planning. So you will see quite often people use RT and RT star in many ground robots as well as aerial robots. So this is actually a plot of the final result. So you have a tree-like structure generated by the sample points, and eventually, if the sum of the samples reaches the vicinity of your goal location, then we reconstruct a path based on the tree. So then, how does the RRT work? Because this RRT is a sample-based algorithm, the first step is to take a sample in the workspace. So usually for a robotic application, the workspace is described by a map. So for example, usually to simplify the method, usually we use a rectangular map or circular map. And by taking a sample, I mean that we generate uniform distributed random points and use those random numbers as the x and the y axis or z axis of the sample point. So basically, if we have an existing tree here, and then we use some random number generators and to generate some x and y coordinates, and then we put the sampling points based on the x and y points here. So this is the first step of the RRT algorithm to generate a random sample. So then the next key step for the RRT algorithm is since it's a randomly exploring sample-based algorithm, we need to grow a tree. Then how do we make a connection between our newly gained sample and the existing tree? This is called something called a steering in the RRT algorithm. So as you can see here, these black nodes are all connected. So we can view this the combination of these black nodes as existing tree. So it's more like an iterative process, right? So when we have a tree, then we move one step ahead and see what our newly sample is in the vicinity of our goal or not. So those black dots are the existing tree, and this green dot is the sample we just made in our workspace. So based on the sampling point, we are going to generate a new node and attach to the tree. So the method is to draw a straight line from a node in the existing tree to the sampling point. And the node picked from the existing tree is based on the Euclidean or some other distance. So we pick a nearest node on the tree to the sampling point as the kind of a reference point. And then after that, we draw a straight line from our nearest node to the sample node to form a straight line. And by specifying the step size of the RRT algorithm, we put a new node on this line, but the distance of the new node to the nearest node is the step size. So as you can see, if we have a existing node, then we just progressively generate more branches and leaves of the tree based on this sample and the step size paradigm. So an important aspect of our path planning is to collision avoidance. Right? So during the sample process and also the new node, also the generated new node, we need to consider whether this path is going to be still going to be interfered with obstacles or not. So in our case, we can simplify the obstacles by using a circle. So if it's a 2D planning problem, we can just say, okay, if we have an obstacle, then we have a circle, and all the paths should not lie within the circle. And another problem is, since we have the new node, then how do we determine this step here lies in the obstacle or not? So we just check whether there's a collision between between the new step and the existing obstacles. For example, if the new step is located like this, then it has a collision, right? Because part of it lies in the circle, and part of it is not. So we consider it as a collision. If it looks like this, it's also a collision because the middle part of the step is in the obstacle. So we still consider as a collision. And so if the newly step we generated looks like this one, so it's away from the obstacle, then we consider this is a collision free. It's also a valid step for the tree. And this one is also valid. So even though if you extend this step, it will intersect, but because we have a fixed length of the step, and if it's outside, if the starting point and end point are all outside the circle, then we still consider it as a collision free and valid step. So the next step after generating the new node is to check whether there is a collision between your new node and all the obstacles. So the steps for detection such a collision is as follows. So what we do is that from the center of the circle, we do a projection of the center of the circle onto the line formed by the new node and the nearest node on the tree. So if the starting point, for example, this S denotes the starting point, and this C is the center of your circle, and this one is the projection of this vector onto your newly generated step. Okay. Then what we'll do is that we will check whether this, for example, if I name as P. So if P is less than 0, or if P is greater than L, so where L is the length of the entire step. If P is less than 0 or P is greater than L, it means that this projection lies outside of the finite length step. So it's pretty much like the so for example, for this projection, if we calculate a P, then either P is greater than 0 or the P is less than 0 or is greater than L, because it lies outside of this step. So if the projection of the center of the circle on the newly generated step, the value is either less than 0 or greater than L, well, we can say that the projection lies outside of this line segment. Then we're going to check whether the start point and the end point lies in the circle or not. For example, for this case, both the starting point and the end point lies outside of the circle. So then we determine this is a collision-free path. Whereas for this one, even though their P is less than 0, one of the point of the starting and end point lies within the circle, then we'll say this path has a collision with existing obstacles. And if P is greater than 0 or less than L, for example, for there is a condition for this line, then we're going to check the vertical distance between the C and the line generated by our new node. So if this distance h here is less than the r plus some tolerance, say tau, then we'll say, okay, there's a collision between our step and the obstacle. So there are two cases we need to check. First, you perform the projection of the difference between of the vector starting from the starting node to the center of the obstacle onto the newly generated step. And then you check the projection P. If P is less than 0 or greater than the length of the entire step, then you check the starting and end points. So if both of them lies outside the obstacle, then it's a collision-free step. If one of them lies in the circle, then there's a collision between your newly step and the obstacle. So there's an invalid step. So you need to do the sampling again. So you just discard the current sample and make a new sample and try and repeat this process. And if the projection is greater than 0 and less than the length of the L, it means that the projection point lies within your starting point and the end point. And then in this case, you're going to check the vertical distance between your center and the line generated by the new node. So you check this H. If H is less than the R plus some tolerance, then there's a collision. If not, it's collision free. So that's how you check whether the newly generated step has a collision with the existing obstacles or not. Yes?
It's only for straight line paths.
Yes.
Quad-order.
Yes. So for quad order case, you can see now we do a simplified treatment. We just use straight line paths to approximate the curved path. So this is a very typical engineering treatment for simple path planning. Okay. Yeah. Any questions about the collision detection? Good. So what we're going to do is to repeat the aforementioned two steps. So we take a sample, we generate a new node based on the nearest node in the existing tree, and then we check the collision. If there's a collision, we discard the current node and do the sampling again. And by doing so, we are going to grow the tree. Right? The tree grows. And then if somehow the newly generated node lies within within the vicinity or a bound around the goal location, then we'll say, okay, we arrived at the goal location. And if that happens, what we're going to do is to backtrack. So for each node, there is we'll have some data structure to record its parent. So from the goal location, we're going to backtrack and reconstruct all the paths all the way to the start point. So in this case, we're going to use a linked list, which I'm going to expand later. So, but in this case, but for this example, here we can just say, okay, for this node, it has a parent index. And this parent will point at this node. So each node will have a parent indicating the node before it is generated. And if we finally have a sample that is located in the vicinity of our goal, we do a backtrack to reconstruct our path. So that's the whole process of the rapidly exploring tree, or RRT. So that's a very high-level description. Then I will explain something in detail using in the code. So you can download the code either from GitHub, and I will upload the code later on Quarkers. You can download and try this. Okay. So the first and also most important topic for actually implement RRT is that we need to pick a data structure. Oh, you see, it's not very clear. So I'll explain. So this is a very typical Python implementation. Or basically, what you do is you define a class in Python. So in this case, it's a tree node. And in your class, you define. You should have two variables to record the position of your node. Right? So after sampling, you're going to record position, and also you should have a list indicating all the child node from this current node, and you have a number recording what is the parent node of this current node. So then you can imagine we're going to grow the tree and we're going to record all the child and parent in this tree node data structure defined by this Python class. So I will explain this later because it's too small in text, how this collision detection works. And the sampling is easy. So just use a built-in function in Python. It's just use a NumPy random package to generate a uniform distributed numbers according to the borders of our map. Okay, so yes. Okay, this is so I'll explain the code a little bit so we can have a very direct and precise understanding of what happens. Okay. Can you see this clear? Okay, good. So this is our data. Oh, what happened? Can I do? I cannot. Okay, let's use a mouse. So this is this tree node class is our data structure for defining a node. So in this tree node data structure, we have two member variables x and y to store the location of the current node. And all the children generated from this node is recorded in this list. So if there's we're going to attach a new node according to this current node, we're going to put the index of the new node to this children list. And then we're also going to record the parent of this current node. So if we generate a new node, first thing we do is to assign a number, i.e. the index of the parent node to this variable. And within the class, we also have two important functions. Basically, it's just to calculate the distance between two nodes. Right. So in this case, we're going to use a Euclidean distance. But if you want to apply the RRT to some scenarios on curved surface, you can modify the distance function accordingly. So this is a very general application. So if you modify the distance based on some distance on sphere, then you can generate your RRT on a sphere. But if I use the Euclidean distance, then I generate my RRT in the flat surface. So this is very straightforward. Just take the square root of the difference in coordinates. Right. And this is how I define map. So in my example, it's a very simplified square map. So I record the coordinates of the bottom left, and the top right coordinate of the map of the square map. So in this case, we can define the borders of our state space. And the sample function here, you can see it's just going to use the NumPy random function to generate a uniform distributed random numbers to get a new sample. And obstacles here is the class to define obstacles. Right. So the obstacle here is also described in a simplified format using the circle. So in the member variables, you can see there is we're going to record is center of the circle as well as the radius. And the important member function here is the collision detection. So I just explained earlier. So what it does is that if for this obstacle, if you are providing the starting index, starting coordinates and end coordinates, and also the tolerance of a line segment, it will first calculate the n0. So n0 is the direction, is a unit vector describe the direction of the line. And the L here is the total length of the current step. So as I explained, we need to make a projection and compare whether the projection is less than 0 or is greater than the length. So here, the L is the length of this step. It's just a very simple Euclidean distance. And the temp here is the projection. So the projection is that we're going to define a vector starting from the starting point of the line to pointing at the center of the circle. So this P is the vector from our starting point to the center of the circle. And this temp, this variable temp is the projection done by doing the inner product between the P and the 0 and N0. So in this case, we're going to calculate the projection. And if the projection, as I explained, if it is greater than 0 or is less than or is less than the length of the straight line, then we're going to check the vertical distance. If its vertical distance is less than the R plus the tolerance, this is a vertical distance. So if the vertical distance is less than the R plus some tolerance, then there's a collision. If otherwise, if it is either less than 0 or greater than the total length of the L, we just check whether the starting point or the end point is in the circle or not. Just as explained in the slides. This is how we do collision detection for a straight line against a circle obstacle. So if you have other obstacles, then you need to figure out your own way to detect whether there's a collision or not. Okay. So that's some kind of a utility class, and then now I'll move to the main program of the rapidly exploring tree. So in this code, the tree is defined, the planet is defined using a class. So it will take the starting position, take the map, defined by using the map class, and we're going to define the starting and the goal location as the input of this class. Then we'll set a maximum iterations. So we'll just keep trying the sample, but we're going to stop at some maximum number of samples. And then you can determine the step size here. So step size is this one. So step size is the distance you increment in the direction of the sample. And then some tolerance. So this goal tolerance is the tolerance to determine whether the sample reaches a goal or not. And the collision tolerance is for the collision detection. So the main procedure is summarized in this update one-step function. So what we're going to do here is that, as explained in the slides, first we make a sample according to the map, right? So this is you just call this make sample function, and then we'll generate a uniform distributed numbers as the x and y coordinates of the new sample. And what we do is that we're going to iterate through all the points in the existing tree and find a point on the tree which has the minimum distance between this node to our sample node. So we just call this find the nearest function. And this find the nearest function is straightforward. So in this case, I'm going to do a recursive style. So we just iterate through all the child node. If the Euclidean distance between the current point and the current node is less than some kind of a stored mean distance, then we're going to update the nearest node index as well as the distance. So just keep looping around the entire tree until we get the index and the minimum distance. Okay. And if we after completion of the sampling and also as finding the nearest node, so this get steer coordinate, well, it's actually the function to generate the new node. So what it does is that it will first find the direction. So so if we have a sample point, if we have the nearest node, what we do first is to calculate the direction of this line as n, and then we're going to increment the coordinate based on the nearest node and n by a step size. So this is how this thing is, what this thing is doing right now. So it uses the find direction function to find the n, and the offset is the n times the step size. So finally it will return the incremented coordinates. So it uses the current coordinate of the node plus the offset generated by the new sample, by the new sample. So after the new node is generated, we're going to loop around all the obstacles in the map, and then we'll perform the collision detection. Okay, so if we find a collision, at least one collision of the current path and obstacle, we're just going to return. So we just discard the current sample and we'll run the sample again. Okay. So if there's no collision, then means that this node is valid. So we're just going to add this node to the existing tree by calling the addChild function. Okay, the addChild function is simple. So it's just to append this current node, storing this while storing the x coordinates, the y coordinate, and also we're going to record the parent index of the current tree, which is the parent index is actually the index of the nearest node in the existing tree. So then if we add this child into existing tree, we're also going to update the child index array of the previous nearest node. So we're going to update the parent node for the new node, and we're going to update the child list for the previous existing node. And then this forms the process of both one-step update. And we're just going to perform this one update until we find a node that is close to our goal location. And then we stop and do the reconstruction of the path. So this is how we do calculate. We're going to iterate based on our maximum iterations. So if we reach maximum iteration and could not find the path, the program will just give you an error. So we cannot find a path. But if we does find a path, it will do this form path. I will call this form path function. So in this form path function, you can say that I first record the parent index by using the last element of the node list. So usually we stop. If we stop because the goal has reached, then the nearest node to the goal is the last element of the list. So we're going to record this parent index, and also we're going to add this node in a temp array. And then I'm going to repeat this process. So I'm going to repeat the process until the parent index is no longer greater than 0. So for the starting node, I put the -1 as a parent index, saying that this is an invalid parent. So if we reach the starting point, then the parent index will become -1, and this while loop will end. So in this case, we're going to append all the node on the path all the way from the goal to the starting location. Then after that, the one important step is to flip the list, because we start from the goal to the start, and for the final result, we need to flip the list, and we need the list to start from the start position to the goal location. Okay. So I'm going to run this that you see a dynamic result. So while exploring the area, you will see it grows like a tree, and then this place is the goal, and this is the place the start. So if it reach the tree, a vicinity of the goal, then it will just call the reconstructed path, and then this red line is a reconstructed path based on the RRT sampling. So, any questions about the implementation? Okay, now this is pretty much how we implement RRT. So, 3 steps. Do the sampling first. Do the sampling first in the workspace, and then based on the sample point and the nearest node on the tree, you generate a new node, and then perform collision detection. If a collision detection pass, you add this new node to the existing tree, and repeat until you reach the goal, vicinity of the goal, and then we do the reconstruction based on the parent index stored in the data structure. Okay. Now we're going to have a quick discussion about RRT star, which is a little bit modified version of the RRT. So I'm first going to run the RRT star, and then you can see visually about the difference. Oh. Never mind. So on the left is RRT, which result we just run, and on the right is RRT star. So visually you will see the difference in that RRT star represents it has like a fan-shaped tree, and while this RRT has like a very more like a stochastic and a random tree. So one primary problem of the RRT is that the path is very zigzag, so it's not quite smooth, and it's not optimal as well. So of course, because of random sample, it is a suboptimal trajectory. So then, can we do it better? So one example, one modification is RRT star. So in this case, we can say, okay, this path is a little bit more smoother than the RRT. Right? So then we can see what the change they made in the RRT star algorithm. The motivation is this. Because the path is zigzag, so sometimes it causes some issues of control. So drones move like a back and forth quite a little bit. So we prefer a more smooth and more optimal path. So the modification we make this is called some kind of a rewinding. So based on the previous sample point, the RRT, we define some radius. So this is a parameter selected manually. You select a parameter of the radius, and you generate a circle around the newly generated node. And what you do is that you iterate all the tree, all the points, all the nodes of the tree, and determine which node lies within this circle. Okay. For example, in this case, we have this one and this one lies within the circle. And in addition to the parent index and the child index of data structure, we also record the cost of each node, which is actually just the distance from the current node to the starting point. So for example, this node has a cost of 93. This point has a cost of 110. And what we do is that we will calculate the Euclidean distance from the current node to all the nodes within the circle. For example, this is the D1, this is the D2. And we're going to, so the cost to this node, if we traveled from each of the node, is actually the cost of the node plus the D, the distance, right? So what we do is that we pick the node with lowest cost. So initially, in the RRT algorithm, we just connected the node to the nearest node. But now we do a circle. We draw a circle, and we check whether there is a shorter path to our new node or not. If there's a shorter path, for example, this one is a shorter path, then we just do not connect this node to the nearest node. But on the other hand, we connect nodes to the node with the lowest cost. So this will be a modification of the RRT. So generate a smoother and some shorter paths compared with the traditional classic RRT algorithm. Yeah, so this is the old path, and if we determine the total cost from this node to the new node is lower, then we change the parent. So we change the parent the new node to this one. Okay, so then we go back to our Python implementation of the RRT star. So the rest of the implementation is almost the same. The only difference is how we implement this rewinding procedure. Okay, this RRT's implementation of the RRT star. So pretty much the same as RRT, where we input the map, the starting position, and the goal location. Okay. And the difference here is that in the one-step update, so this is a main function we're going to call. It's called a one-step update. So we're going to do a sample as the same step in the RRT, and we're going to find the nearest point based on the Euclidean distance. And also we do the steering to generate a new node. And then we're going to check the collision. So all the steps here are all the same as the steps in the RRT. But if this current node passed the collision detection, we're going to find all the neighbors of this this newly generated node based on our rewinding radius. Okay? So this is a function of detected all the neighbors. So basically, we're going to have a neighbor index list, and and then we iterate through all the nodes in the current tree, and if the Euclidean distance of the node is less than between the node and the new node is less than the rewind radius, and also there is we also perform a collision detection between the new node and all the node we're going to check within the radius. So if both check pass, we're going to treat this as a valid neighbor points to be investigated in the rewinding procedure. Okay, so after the neighbors are found, we're going to perform the rewind procedure. So basically, we're going to calculate the current cost. So the current cost is the cost of the node. So this is the cost of the existing node plus the Euclidean distance. This is the Euclidean distance from the new node to the existing node. So we have the current cost. And also, this is the parent of the current current node. So if the cost is less than, so if we just iterate through all the neighbors in the neighbor list, if we found a neighbor with a lower current cost, then we update. Okay. So then we'll generate a new cost and a new parent for the new node, and then we perform the add child function to add this new node. While and also in the add child function we need to store the new parent and also the new cost of the new node, and then we're just going to update the node list, and then everything else is the same as RRT. So after that we iterate. If we found a point that is close to our goal location, we do backtrack to form the path. Okay, so run this thing again. So let's see, like it's more like a fan structure, right? And the path is a little bit smoother. Well, probably statistically speaking, it's not always the case, but statistically speaking, it has a better path following result, has path result, and also the path is smoother than the RRT. Okay, so this is a path generator. So it's not always the optimal one because we do a random sample. Okay. So any questions so far? Yes. Oh, what's that? Step size is a parameter you need to set.
Is it varying for every?
No, it's a fixed.
The diagram.
You mean the left or right?
Right.
Yeah, because we perform a rewinding, right? So because so the distance from each node is not the step size anymore. It's because we have this radius. Okay. Any questions? No? So I will upload this code later to Quarkus, and you can just use that in your project. Okay, we can take a break. Yeah, going to introduce you the other part, the other half of this lecture is called the A-star algorithm. So it's a search-based algorithm. So compared with the RRT, the A-star will give you a deterministic result according to the map, rather than sample-based. Okay. So A-star was developed in 1968, created as part of the Shaky project, which had the aim of building mobile robots that can plan its own actions. So this is a very famous picture of very old mobile robots. This method was developed by Niels Nielsen using the graph traversal algorithm. So what it does is that it start from a specific starting point and use some constructed cost functions to systematically explore using the breadth first search to determine the optimal path. So there is no sampling in this A-star algorithm. So this is a kind of a result you can get from the A-star algorithm. So this is a start point, this end point. And usually it is applied to discretize a map. So if you have a continuous state space, you need to discretize your continuous state space to discrete points, and we can perform A star. The red dots here are obstacles. So in A star, you explicitly define the obstacles by setting some values to the grid on the map. And the most important element of A star algorithm is the cost function. We denote the cost function as Fn for node n. So for each node, each grid on the map, we assign it with some cost functions. So the total cost is called F, and it is a summation of two cost functions, G and H. So G is the cost from the starting node to the node n. So you can view this as a distance traveled from the starting point to the current point. But H here is something special. It's something called a heuristic cost. It is actually a kind of estimated distance from your current location to your goal location. So your cost is a combination of the paths you have traveled and the paths you have not traveled. And we're going to explore the map based on the total cost of these two cost functions by using something called a breadth first search, BFS.
I just wonder with the graph on the bottom right, lock those are obstacles, correct?
Yes. So basically, just expand your search area gradually based on the cost functions, and if the search area some points contact the goal location, the reconstruct the path. So the heuristic cost is an important aspect of the A star algorithm. So the one important thing is that this is non-unique, so you can pick your own heuristic function. But usually there are two candidates. One candidate is called Manhattan distance. So basically, it's just the difference in x, the summation of the difference in the x and the y directions. So it's a summation of these two straight lines. It's called Manhattan distance. Euclidean distance is straightforward. It's just the distance from your goal location to the current node. So you need to pick either one based on the traverse pattern. So if you can traverse diagonally from a grid point to another, you need to use the Euclidean. Otherwise, you need to use the Manhattan distance. Now, the G cost here is straightforward. So, for example, if the parent node of this node has a G cost of Gm minus 1, and the distance between the current node and the node n is D, then the G cost of the node D is just a summation of the cost of the parent node and the Euclidean distance between these two nodes. Okay, this is similar to the cost we used in the RRT star algorithm. Now, one of the problems is that for a grid map, for example, if we want to find the G of this point in the center, there are many possible ways to travel from the start point to the G through all the neighboring grid. So in this case, if we have the G cost of all the neighboring grid, what we do is just to pick the neighboring grid with the lowest total cost. So, for example, if node I, node I plus 3 has a cost of 81, and then we just pick and we calculate the d the total cost by as a summation of the d plus 81. So if this one is still the lowest one within all the, so we're going to iterate through this process through all the neighboring node. If this one is the lowest one, we're going to just pick the summation of this one as the g cost here, and we'll set the I plus 3 node as the parent node of the current node. So this is similar to the rewinding process in RRT style. Okay, so now since we have the definition of the cost, g cost and h cost, then how do we do the search based on the cost function? So the name of this search is called the breadth-first search. It's a commonly used terminology in computer science. It's called, or we just say the BFS. So before I introduce the detailed algorithm, so there are some definitions we need to clarify. For a grid map, there are four types, not 3 types, 4 types of nodes. So the red node here is called inaccessible. So usually we just define the obstacles by using the inaccessible nodes. And the blue ones are the explored nodes. So this node has already been explored. So we're not going to explore again because this one has been visited. And the green nodes are known to be explored. So it's more like a border of the explored nodes. And also the black nodes. So those nodes has not been explored yet. So from this dynamical figure here is that you can see that the red node here is actually our blue node. So inside this red area is a node that has been explored. The green ones on the border are the nodes to be explored, and all the white node and the nodes has not been explored yet. So the first step of A-star algorithm is to construct 2 different lists containing all the nodes. One is called an open list. Another one is called a closed list. So the open list, we're going to put all the green ones in the open list. And we're going to put all the blue ones in the closed list. So the open list is a list that telling you all the nodes that has not been explored, to be explored. And the closed list is telling you those nodes has already been explored. So we're not going to repeat the explore again. Then what do we do is to use the breadth-first search and also in conjunction with our cost function. So this is one step of the A-star algorithm. So the figure on the left is you can see you can view this as a map before our one-step update, and this one on the right is the map after the one-step update. So what do we do is that in the open list, so among all the green nodes, we pick the green node with lowest F cost. So the total is a summation of the G cost and your heuristic cost. For example, this one has the lowest F cost, which is 89. Then we're going to remove this node from the open list and put it in the closed list. So means that we're going to explore this node. And here I just label this node as blue. So we have already explored this node, and we'll put it in the closed list. And after that, what we do is that for this node has just been explored, we're going to check its neighbors. Okay. So by checking the neighbor, I mean that we're going to recalculate the G cost for all the neighbors. Because before the update, this neighbor, the parent of this node is from this node, so which has a G cost of 90. And if we explore this node and somehow we find the G cost is 80, which means that it has a lower G cost, we're going to perform some kind of rewind process here. So we're going to update the G cost and also the F cost based on the newly explored node. So we're going to explore all the nodes. If this node is already in the open list, which is marked as green, we're going to update the G cost if the G cost from the current node is lower. And for this node, black node has not been explored yet. And then by exploring this node, if this one has not been explored yet, then we just calculate the G cost and add this node into our open list. So we grow the closed list, we propagate the area of search by using this kind of BFS strategy. So so every time we check whether we have available points in our open list, which are the green points. And if we do have one, we pick one with lowest F and explore that node. And also by exploring, I mean that if there are some unexplored area, we're going to assign a cost to the unexplored area and put all the newly explored node in our open list. If this node is already in our open list, we're going to check whether we have a better route to that node by recalculating the G cost. Okay, any questions? Then what we do is repeat this process until somehow one of the newly explored node is exactly our goal location. So we just propagate our search area repeatedly, and then hopefully we can find our route to the goal location. And after that, if we do reach the goal location, for example, goal location is here, we do the same thing as we have done in the RRT. We're going to reconstruct the path based on the parent index. So we can trace back from the goal location using the parent index stored in the data structure of each node. We reconstruct the path. So it's a backtrack to construct the path. Okay, now back to the MATLAB implementation. So I also put this MATLAB code on Quarkus. You can use it in your project. Okay. Now, the first thing we're going to do here is to generate the map. So, because this is a search-based, discrete search-based, you need to discretize your map first. So, for example, if we want to use it in drawn path planning, you probably need to discretize the time map to some points and then run this algorithm. And also the gates can be treated as inaccessible points. So yeah, obstacles. So this is there's a map, and if we want some part of the map to represent the obstacle, what I've done here is that I just set it as 1. If it is accessible, then it's 0. So you can use a binary number to determine whether this place is accessible or not. These two are the start and the end point of our location. Okay, so I run this. Okay. Takes a while. Okay. So this is a final result running this code. Okay, as you can see here, so you see red, right? Those red are the obstacles, and this is the start. This is the goal location, and you have some obstacles here. And this is an optimum path planned by the A-star algorithm. So as I said, one of the more important cost function of the A-star is called a heuristic cost. It's an H cost. Then this function calculates this cost. It's called a UTL's heuristic cost. And we have two candidates here. So one is Euclidean distance, which is the square root of the difference, right? And then the other one is Manhattan distance, which is the summation of the x and y difference. So the criteria of picking either of this is whether you allow for diagonal transition. It means that you can only allow the drone to move up and down, right and right. But if you allow it to move diagonally, then you need to use Euclidean distance because it represents the heuristic more accurately. So the first step we're going to do is to this is our open list. So just never mind about names. So the naming here is terrible. So this one is the open list. Okay. So before the calculation starts, you need to put the starting point into the open list. So this is the very beginning of the exploration, right? So this is and also this is a coordinates. And because if you are the start point, you do not have a G cost. So I only put the H cost here to represent the H and F. So the G cost is 0. And close list is empty. So right now we haven't explored anything yet. So never mind about all the remaining. So we're just going to grab the essential part of this program. So what we do here is that we're going to run a while loop. So iterate until we find until if there's no solution possible. If there's no solution possible, or if there's no accessible points anymore, then we're just going to display an error signal. If the while loop stops before every point is exhausted, it means that we find the optimal path. Okay. So the first thing we're going to do is that we just pick a point in the open list according to the F cost. So the data structure I use here is very simple. It's just an array to store the coordinates, all the costs, and the parent index. So in the lowest F index, I'm just going to do a minimum search, right? Search the minimum index with the F cost. And if we found if there is something in the open list, we're just going to append this point in the closed list. So we explore this node. By exporting, I mean that I move this point from the open list to the closed list. And here, this is an append action. This is a delete action. So I delete this point from the open list. So then we're going to do the BFS algorithm. So first we're going to compare whether this point is actually our goal location or not. So if we compare the location, if this is our goal location, stop the while loop and reconstruct the path. If it is not the goal location, as I said, I do BFS. The first step is to export all the neighboring points. So if the neighboring has not been explored yet, we calculate the neighbor G cost and H cost and F cost and put the neighbor point in the open list. If the neighbor has already been explored, then we update the G cost if we have a lower G cost. Okay. So this function is going to give you all the, so it's called a UTO cost neighbor. It's going to generate all the neighbors neighbor index based on the definition of your map, and also the current point. And for every so it will also give you the G cost of every neighbor around the current candidate point. And what we're going to do is to update the F cost, right, for every neighboring points. So after that, we need to so according to this slide, if it has the lower G cost, we need to update, and if it's not in the open list, we need to put it in the open list. So this is how this part is done. So it will first calculate whether your neighboring points is in the open list or not. So this function will determine whether the neighboring points is in the open list. If it is in the open list, we're going to compare the G cost of the G cost generated by the newly explored node with the old ones stored in the open list. Just like I explained in this figure. So if we find this one is in the open list and has a lower G cost, what we're going to do is just going to update the F cost, the G cost and the F cost, and as well as all the parent indexes. If this index is not in the open list, so it's in the unexplored area, the treatment is simple. So we just append this point in the open list. Okay, and this is the end of the while loop. So it means that we do this process again and again until we find the path to a goal, or every point is exhausted, and we return an error signal. So if we do return with solution found flat, what we do here is that we're going to reconstruct the path. So which one is the function? Here. It's called a reconstruct the path. So this is also the equivalent to what I've done in the RRT star algorithm. So basically, based on the parent index, we're going to compare whether the parent index is invalid. So if it is invalid, it's like -1, -1. So if it is invalid, it means that it is a start. If it's not start, we're just going to do the while loop, and we'll just append the index in the result list, and then we find the parent of the newly found node, and we repeat that process again to backtrack to get the planned path. So any questions about the entire process? About the BFS search? Okay. So after that, you can modify this one. So if you do the tunnel, I think you have a gate traversing task, right? Is that the okay? So if I have a gate traversing task, then you need to kind of design a tunnel on the map based on the discretized map. So you basically just allow one tiny tunnel from the starting point to end point, and you run A star algorithm. Okay, so I think that's pretty much for the course for this lecture. So I'll just do a quick recap. So in this lecture I mentioned two past planning algorithms. One is RRT and modified version RRT star. It's a sample-based algorithm, so you might need to run multiple times to get an optimal solution, because statistically only statistically better than the deterministic one. The other one is search-based, so it's A star algorithm, and the search-based the algorithm requires you to discretize the map first, whereas the sample method does not have this requirement. So you need to discretize the map, and then you need to assign a tunnel if you want to do gate traversing to the map, and then you're going to perform the A star algorithm. Okay. Any general questions about implementation? No? Yeah. Good. I think that's pretty much all the content of its lecture.